All right, so the last little bit of Unit 3 is up at the top, and we need to talk about those rules that we just used for determining, for determining the electron energy levels. And the first one is they're going to fill up the lowest energy level first, and that is the Aufbau principle. So we start from the bottom and work our way up, lowest to top. Each suborbital contains a different number of orbitals. An orbital represents a pair of electrons, two spins. Well, this one doesn't really need no more than two electrons, arrows in one orbital. And this is the Pauli exclusion principle. In other words, we can only have one spin up, one spin down. Electrons have opposite spins in orbital because the negative charges repel each other. If you have more than one orbital in a sublevel, one electron goes in each orbital before you double up. So that means we're going to, give, when we looked at those boxes, we'll put an up in each one before we go back and put a down in, and that's Hund's rule. So a couple things you need to know. I know it's difficult to see, but Hund's rule, that's the everything gets an up before we get a down. We can only have one up and one down in each, and each orbital is a pair, and we start with the lowest, and that's Aufbau. All right. From here on out, we are now going to move on into Unit 4. Okay, so without looking at our notes, give the polyatomic ions, including their charges. These are all pretty much our 8s. Sulfate, chlorate, carbonate, phosphate, nitrate, silicate, and now we have the extra little guys, our ides and ammonium, cyanide, hydroxide, and peroxide, and ammonium. So let's start with our only positive. The only cation we have of our polyatomic ions is our ammonium, NH4 plus 1. If you see NH3, that is ammonia. It is not a polyatomic ion. It is a molecule. All right. Let's finish doing the rest of our crazy guys. Our cyanide, CN together is a -1. Hydroxide, OH together is a -1. Peroxide, O2 together is a -2. Now that is different. O by itself in oxide is -2. Peroxide, if you can think about it, this is the O has 1. Each has a -1, but they're together, so it's a -2 combined. Okay, so sulfate, carbonate, chlorate, nitrate, and silicate. Let's do it this way. Let's write all of our -1s, like our chlorate and our nitrate. So our -2s are our sulfate, SO4, carbonate, CO3, which is also a -2, and silicate, SiO, let's see, catch me if I'm wrong on this. I believe silicate is also a 3, but I'm going to get and check that before I tell you, and we'll go with it from there. Yep, 3. So it is a -2, and notice phosphate hasn't been. Phosphate is our PO4, and it is our only -3 polyatomic ion. And so why is it okay that I'm only asking you to memorize the 8s? It's because the 8s always have one less oxygen than the 8s. So Phosphite, PO3, same charge, -3. Chlorite, ClO2, same charge, -1. So when we give a formula for a compound such as CaCO3, we always put the metal or call it a cation, the one that is a positive charge. Subscripts in formulas indicate the number of what? What does that 3 there, the subscript, mean in the CaO3? It's the number of atoms in the molecule. In the molecule. Okay? If a compound is formed by a metal bonded with a nonmetal or a polyatomic ion, the substance is ionic. If it's two nonmetals, the substance is covalent. Now, it can be polar covalent or nonpolar covalent, but it's always covalent. And if it's formed by two metals, we just call it a metallic bond. If the electronegativity difference is greater than 1.8, the compound is ionic. Remember, we did cover all this in class the other day. If the electronegativity difference is between 0.6 and 1.8, the compound is most likely polar covalent. There are a few that are sort of hanging in there on the edge of ionic and polar covalent. These two can act very similar to each other. Remember, some of our acids are actually polar covalent. Something such as HCl is really polar covalent, but when it's in liquid form, when it's in aqueous solution, it acts very ionic. If the electronegativity difference is less than 0.6, this is our nonpolar. In other words, all the charges are balanced in a nonpolar covalent. So polar, if you need to look up this in Unit 4B notes, but polar means our charges are not evenly, they're unevenly distributed. One of the atoms or more in that molecule are pulling the electrons closer. And so that makes that guy act more negative and the other guy act more positive. So if you think, let's put a let's do a water. So there's my oxygen, there's my big oxygen, and it's attached to a couple of little hydrogens. And the big oxygen pulls the electrons. The electrons get pulled in really close to the oxygen, making that oxygen act very negative. And these little hydrogens then get left without, and so they're acting sort of positive. In something like carbon dioxide, and I'll just draw the Lewis dot structure for that really quickly. Can you guys see how balanced that is? It's all really balanced. So this guy is more likely to be nonpolar, and the charges are fairly evenly balanced. This guy and his sort of off shape is going to be polar. So nonpolar is even distribution of charges. And we did these in class, but sodium, let's just think, sodium's over here, fluorine is over here. Those are way on the opposite side. If you do the math from the electronegativity here, you see those are definitely ionic. And we don't really even need to do the math. We know fluorine is incredibly electronegative and sodium's on the other side. A metal and a nonmetal, it's ionic. S and O are right here. They are both nonmetals. This is most likely, and since they're really close to each other, this is probably nonpolar covalent. B and Cl. Right here, B, Cl. Well, they're both nonmetals, but they're probably polar covalent. They're a little bit further apart. Mg and I. See, Mg would be right here. I is way over here. That's another ionic. Zn, which is right here. Oops, you guys can't see. Right here. Zn. And Br, bromine, over here. It's a metal and a non-metal. If you do the math, it shows up to be within that polar covalent. But once you get a metal in there, we'd probably more likely define this as ionic, but it's sort of on the borderline. And H and Cl, remember, these are polar covalent. Even though it is an acid, when it's as a molecule, the big Cl pulls all the electrons in really tight, leaving the H's, just like H2O, leaving the H's really positive. Okay, so anyway, we will continue with naming in our next video.